So can someone now tell me which form of energy is being transferred at the inlet here? Here, because kilowatt only means rate of energy transfer. It doesn't tell you which form. So I was hoping that you will remember this, but this is actually, you see this shaft. You see, if you look at this, this indicates that it's work transfer. Yeah? So it's work transfer in, work transfer out. Yeah, this one, and this one, Q dot, is the heat transfer rate, and heat transfer rate with a I mean, because it's negative, so it must be out of the system. So we know these three quantities. Yeah? And we know the temperature of the boundary. This is the temperature of the boundary, TB. This boundary, this system boundary. And you want to know, okay, now because you have this gearbox, and inside this gearbox you have gears, and whenever you have gears interacting with one another, you can imagine friction. So you can now expect some entropy production. Sigma must be produced as a result of the interaction of those two gears. There are other phenomena, of course, in the gearbox. There may be fluid, cooling fluid, and so on. So there are many irreversibilities possible here. So let's see what is being asked here in part A. In part A, okay, so in both parts you're supposed to calculate the entropy production rate, sigma dot, yeah, in these units, kilowatts per Kelvin. And in part A, the gearbox is your system, so it's this one. In part B, you will have to change the boundary. You will enlarge the system. You will have a larger boundary, and you will see why we need that. Yeah, that will have a purpose. Okay. So if Q dot is minus 1.2 kilowatt, let me just label this so that we know what we are doing. This 60 kilowatt, you can think of it as W in dot work transfer in, and this is work transfer out. This one, work transfer out. And maybe instead of writing in or out, maybe we can just write the just label the inlet and exit. So let's label the inlet as 1, and let's label the exit as 2. So it's W1 dot equals something and W2 dot equals something. And now we are not dealing with cycles here, so the sign must represent whether it's in or out. Now this is work done by the system, so this would be plus 58.8 kilowatt, and this will be minus 60 kilowatt, because this is into the system. Q is already given. Temperature of the boundary at which you have that heat transfer is also given, and we are supposed to calculate sigma dot. How do we go about it? Yeah, we just need to use this law. I just reproduce this. So now we are actually solving that example. So can you tell me which of these terms can be set to 0 based on the diagram? Yeah. If you look at the diagram and if you look at the assumptions, there is also do you have any other thing? Okay, Of course, those standard assumptions, kinetic energy change, potential energy change, that is zero. So in this equation, we don't have that. Yeah. So J will go from 1 to 2 because there are two. No, in this case, this the whole boundary, all the boundary is assumed to be at the same temperature, TB, which is given to us. So this summation will be just one term, yeah? So I'm now writing that down. I'm now writing this equation down. On the left-hand side, I have ds over dt. On the right-hand side, I have q dot over TB because there are no portions. I have this summation j is equal to 1 up to some number only if my boundary, this is what I discussed last time, if my boundary has many portions and at each portion, let's say I have T1 here, T2 here, T3 here, then I need this summation. But in this example, the whole boundary is just labeled as B, and there is one temperature TB, so this will be just one term. And this will be yeah, y plus sigma dot. Yes. So how do we calculate that? Okay. I think because this is example 2.4, you cannot explicitly see that part from this description. You have to go to example 2.4, and I can say that because of this description, we don't need to go to example 4. You see, what is known here is that the gearbox operate at steady state. Yeah. Now this steady state must have been mentioned in example 2.4 if you go there. Yeah. So we don't need to go there now. We just incorporate this steady state thing here. Now that steady state means that all the properties must not change with time. So in this equation, which term must be zero?
ds by dt?
Yeah, because that's a property, yeah. So that must be zero. That's the meaning of steady state. Which means, and what is the unknown in this equation? This is the unknown.
Sigma.
Sigma dot. Remember, rate of, evaluate the rate of entropy production. So which means that sigma dot now equals, this side is zero, so it must be minus q dot over TB. You know q dot and you know TB, just plug those two values. Huh? Q dot is given in the diagram, which is negative, so minus of that will be 1.2. Yeah, so I'm now evaluating this here. Because of that minus and minus, it cancels out, so you have 1.2 kilowatts, and in the denominator you have TB, uh, which is 300 kelvins. So that you can do that. Okay, that's your answer. And check, make sure that this is non-negative. Yeah. For example, if you forget to notice this minus sign or that minus sign, you will get a negative answer, and that is wrong. You should be able to see that. So the value is 4. Let me just write that value. It's 4 to 10 to the minus 3, I think. Yeah, kilo watts per Kelvin. Now let's enlarge the boundary now. Enlarge the boundary and enlarge it as much to a point where you see that the surrounding, because the temperature of the surrounding will also be affected by this heat transfer. So because of this heat transfer out of this gearbox, you can expect the near uh, portion of the surrounding to have a temperature change. So as you move away from the surrounding, that temperature will get smaller and smaller, because parts of the surrounding away from the gearbox will have a smaller temperature. Yeah? So when you see that temperature 293, that declare that as your boundary. Yeah? So now you can imagine that this is now your boundary. This is your now you have this enlarged system. Within this system, you have this gearbox. So within the system, the temperature changes. Yeah, changes with respect to space, not with respect to time. Remember, steady state doesn't mean that properties cannot change with respect to space. So this variation is with respect to space. So here you have a larger temperature, here you have a smaller temperature. This is a temperature gradient, not a temperature rate. And now you want to re-evaluate that sigma dot for this new system. Yeah. So we will actually use the same formula. Heat transfer doesn't change. It's still 1.2 kilowatts. And that minus sign still cancels out. Yeah. So it has nothing to do with where is the boundary. But the temperature now, the denominator is this time, instead of 300 Kelvin, you have 293 Kelvin. So if you evaluate this, and you can check the answer yourself, that turns out to be 4.1 multiplied by 10 to minus 3 minus third kilowatts per Kelvin. Yeah. So this is sigma dot for part A, and this is sigma dot for part B. So there is a difference. Yeah, there is a difference. Which of the entropy production rates is larger, part B or part A? Part B is larger. Yeah. Now, how do you interpret this result? That value arises, and we know sigma dot represents the production rate. So that is the irreversibility within the gearbox. Now this is the irreversibility for this larger system. Now what have you added? You have added part of the surrounding, which was there. Now it's part of the system. Now there you have a difference of temperature. Whenever you have a difference of temperature, there will be transfer of energy. Now you're not calling it heat because the bound it's within the system. So you just call it transfer of energy, or some thermal interaction, and that results in because it's within the system, you cannot call it entropy transfer. This you will have to classify this as entropy production. Entropy production. So you can see the difference between these two. The difference between these two is 0.1 multiplied by 10 to the minus third kilowatts per Kelvin. This is the entropy production. And if you look at this in part A, you can say that, okay, in the surrounding, in the nearby surrounding, entropy is also produced. But that is insignificant compared to the entropy produced in the gearbox. So you can easily ignore this now. This is something you can ignore. You can go back to part A and you can say, okay, the entropy production in the surrounding is insignificant. So just by changing the boundary, you saw that. Okay, one more thing. what did I assume when I subtracted this entropy production rate from this entropy production rate? When can I do that? I discussed this last time. I can only do this with quantities that are with quantities that are um, extensive. I can't do that with intensive properties. So for example, if this were pressure, you cannot add or subtract pressure at different points. You can only do that at a single point. And this is why, and if you have understood this point, you remember when we go from extensive properties, when we divide an extensive property by, let's say, mass or volume or number of moles, number of moles, you have an extensive property, you divide it by mass or by number of moles or number of kilomoles, to be very precise in this book. You give it a name. If you remember, you call it specific property. Specific property. You don't call it intensive property. That's the reason, because intensive property has a different meaning and specific property has a different meaning. They don't depend on size, but specific properties can be converted. These specific properties can be converted back to intensive property, and you can even add them at different points. So now we are in a position to discuss the direction in which a process has to proceed. There are many natural processes, and you don't know if you want to predict how they will proceed. For example, there is a chemical reaction. Let's say there are reactants and there are products, and this reaction can go from A to B or it can go from B to A. So which of these two directions is dominant is something which we want to discuss here. And this is just one example. There are many other processes for which you would like to know the directionality. So, and for that we need the increasing entropy principle. But before that, you should already actually you should start by appealing to the first law of thermodynamics. First law, and then the second law. So what the first law does is that it puts a constraint on the direction in which a process must proceed. And that constraint is very simple. You enlarge your boundary. If you want to analyze a process, you choose a boundary in such a way that the enlarged system is an isolated system. You make it isolated because for isolated systems, you have a simple law. You don't have to consider what happens at the boundary, because in an isolated system, all the interactions at the boundary must be absent. No mass transfer, no energy transfer, and so on. So if you, and this is in your hand, you just define your boundary in such a way. If you do that, then you can easily say that the change in energy of an isolated system, remember this subscript, must be zero. So that is the constraint or constraint. Every process must follow this constraint. But this is not enough. What this constraint mean is this. Remember, energy is also an extensive property, which means that if you have enlarged the system so that you include the whole universe, then the actual system with which you started, let's say this is the actual system, let's call this system, and this is now the surrounding, and this complete system, which is the isolated system, you can think of this as either the whole universe or enough larger system which can be considered as isolated. So now in this enlarged system, you have two parts: your system, your surrounding, and energy is an extensive property. So this change in the energy of an isolated system can be broken down into two parts: the energy of the original system, yeah, and the energy of the surrounding. You can do this because energy is an extensive property. So if you want to expand this, okay. So now why is this more useful? Because this is your primary object of interest. So you can say, okay, if I want a change in the energy of the system, whether it's positive or negative, what you are claiming here, or what the first law of thermodynamics is dictating here, is that for any process, because whenever a process, you want to say that, okay, the system must proceed in this direction. In other words, let's say it starts with one state and it ends up in another state. So in so doing, the first law dictates that as a result of this process, the change in energy of the system must be balanced with an opposite change in the surrounding, because they both must add up to zero. So if you want an increase in your system, the of energy, there must be a decrease in the surrounding. Otherwise, you don't get this zero. But this is not enough. There are many processes um, which are allowed by this first law, but they still uh, do not occur. So, which means that the first law is a necessary condition for a process to proceed, but it's only a necessary condition. It's not a sufficient condition. Just because a process does not violate the first law of thermodynamics doesn't mean that it will proceed. And that's why you need second law of thermodynamics. And so far we have established that that second law of thermodynamics is more useful if it is expressed in terms of entropy balance. So now we need a second condition, and that is the entropy balance. For any process to proceed, again, you enlarge your boundary, think of an isolated system which contains your system of interest, and there you can say that, okay, the change in the entropy of an isolated system must be equal to the entropy production. This is the entropy production. Why? Because for any isolated system, the entropy transfer must be zero. There can be no transfer. No mass transfer, no heat transfer, so therefore no entropy transfer. So the entropy of an isolated system, which is the quantity on the left, must be equal to the production, entropy production of that isolated system. Now we can do the same as we did before. Because entropy is an extensive property, so I can now break this left-hand side down into two parts. I will have change of entropy for the system of interest and change in entropy for the surrounding, SURR. That equals, remember, in the previous case, that change was equal to zero because it was energy, but in this case, it must equal to the entropy production, the overall entropy production, yeah, both within the surrounding and within the system. So, and because this must be positive or zero in the ideal case, so this is the constraint imposed by the second law. Yeah. Now remember, these two, it is possible that one of the terms is too positive. Let me write many positives to say that, okay, it's too positive, and the other term is, let's say, negative. Yeah. but less negative, so that the overall effect is positive. So that's possible. And this is what we mean by what is called the increase of entropy principle. So now if you want to know whether a process such as a reaction in a particular direction will be physically possible or not, yeah. So you have to apply two conditions. First, you apply first law of thermodynamics, it must not violate, but that is only a necessary condition. A sufficient condition is then the entropy, increase of entropy principle. For any real process, because you know that that reversible process is only ideal, any real process must have irreversibilities. So basically, it is not this must be greater than. Yeah. For a physical process, this must be positive. It cannot be zero because zero means ideal, and ideal is not possible. Now, all this discussion can be understood by this example. इस एग्जांपल में आपको पता चल जाएगा कि why we need those two laws, the energy balance and the entropy balance. In other words, the increase of entropy. So in this example, we have a tank. You see the tank here? This is the tank. And this is insulated. You just assume that, okay, it has been insulated from the surrounding. So you can think of this as an isolated system. This is an isolated system. Yeah. You have included enough part of the word so that you can ignore the interactions with the rest of the surrounding. So here initially you have a metal bar. This is the metal bar, and if you read this carefully, you will come to know that this metal bar is initially at a temperature of 1900 degree Rankine, and this M is for metal and I is for initial. So this is the initial state of this metal. Yeah. If you think of metal as a subsystem, so the metal bar has TMI, metal initial temperature is 1900. MM is mass of the metal, and that is 0.8 pound. It is also given there. Actually, this is how the question starts. And you assume this metal to be, for this analysis, is there any question? No. For this analysis, you assume the metal to be incompressible, even if it's not mentioned. Yeah. It's typically, we assume incompressibility not only for solids, but also for metals. So, which means that the specific heat, C, specific heat is the same. You don't have to write Cp or Cv, it's just C. Okay. Now that C, of course, you will need one C specific heat for metal and one C for water. So we write Cm for the specific heat of the metal and Cw for the specific heat of the water, Cw. Now this metal bar is very hot. Remember, see the temperature, 1900. Rankine is a large temperature, and it is inserted in water. That water is initially at 530 Rankine. ये आप लोगों को आवाज आ रही है?
Yes, sir.
ये किसका ऑन है माइक? बंद करें अपना माइक, सॉरी. ओके, मेरे ख्याल में वो एक स्टूडेंट है, शायद उसका माइक ऑन था, ठीक है। तो so some of you please take a note, and if there is anyone whose mic is not mute, you actually bring that into my notice, and then I'll mute that.
Okay, sir.
Okay, thank you. So now in the surrounding, no, not in the surrounding, the immediate surrounding of the metal bar, if you think of the metal bar as the subsystem, the immediate surrounding is water, and the initial state of water is given to you. All these values: temperature of water initial, the specific heat of water, and the mass of water. So if you compare these quantities, there is more mass of water than the metal, number one, and water has a larger specific heat compared to the metal. That's also something you need to note. And the metal rod has a larger temperature compared to water. Okay, so based on this data, what do you predict? What will happen when you bring these two objects into contact, water and metal? What will happen? I want a qualitative answer from you so that we start solving the problem after that. What can you say qualitatively? What will happen?
Heat transfer between the subsystem and surroundings, so thermal equilibrium is reached.
Okay, yes. So, but be very careful, because this is your system boundary, so you cannot use the word heat transfer. Everything is happening within the system.
Sir, if we specifically say the subsystem will...
For the subsystem, you can do that. Okay, yeah. But
Okay.
when you write the balance, energy balance and entropy balance for this overall system, you make sure that you don't use the word heat transfer there. Okay, no heat transfer, no mass transfer, no entropy transfer. There's things only possible at the boundary, but we will come to that. Don't worry. Okay, for the isolated system, it's very easy to write down the equations. But first we need to know what is asked. What is the question? In part A, we're expected to determine the final equilibrium temperature of the metal bar and the water. Of course, these two will interact in such a way that finally, and let's represent that by F, finally I will have a temperature Tf of the whole system. That will be my equilibrium. So if that is Tf, can you, now let's write the energy balance. Remember, before this example, I told you that we must start with energy balance. So how do I write energy balance for this system? Delta energy of this whole isolated system must equal 0. Yeah. Now, because this system has two subsystems, and because energy is an extensor property, so I can now say delta energy of water, W, or maybe I just start with M for metal, and delta E of water, W for water. So before I plug values, you can say something at this stage. At this stage, what you can say that the energy, you expect the energy, or to be very honest, total internal energy, yeah, because you can't, there are no, actually, there is no work interaction and no kinetic energy, potential energy, all those can be ignored. So the internal energy of the metal rod will decrease because it's hot, and the internal energy of water will increase, and these two will balance one another so that the overall change is 0. That's what you expect. And I can also say that because all the others, all the other forms are not there, so I can replace this with this E with delta U, and this E also with delta U, internal energy. Even here I can say internal energy if I know what I have ignored. So can you now connect this delta U and this delta U to Cm and Cw? Here is the consequence of the assumption incompressible. Because you assume both the metal and water to be incompressible, the differential change in the specific internal energy must be equal to, of course, U must be a function of temperature only. That's what is meant by incompressible. What that means is that the change in internal energy must be the constant specific heat times the change in temperature. Now this must be done for M separately, and this must be done for W water separately. So this will be Cm times dt for metal and Cw times dt for water. This is how you will start. Okay, which means that I can now, and this is actually this small u is for specific. Here I need the total energy, so I must multiply both of these by the masses. So mass of M, mass of metal, mass of water, mass of water. So I can now plug these values there. So the equation I have will be C M M M. I need mass as well as the specific heat, and I'll multiply that with the change in temperature. I assume this to be constant, yeah. So I don't need to integrate. It will simply be the change in temperature. So T final of the overall system minus Tmi plus, here I need C water, M water, T final, Tf is the same for both, minus Twi. This must equal 0. Actually, this is change in internal energy for water. The first term is the change in internal energy for. Okay, you can now solve this equation if you want. But let me give you a tip of simplifying your calculations before you plug in. Because if you right away plug in values here with all those units, it can look very nasty. So if you see such an equation, and if you look at these units, you can simplify and you can actually have a very clean process of solving this problem. Now, think about this. I have mass in the first term, yeah, and I have mass in the second term, and I have 0 to the right. So what can I do? What if I divide the whole equation? Now I'm doing this without putting any values, okay? What if I divide the whole equation by the mass of metal? So I'll get rid of this. I got rid of one thing without even plugging the values. Can somebody now tell me what is the mass of these? What is the ratio of these two masses? MW over M mass. You see, in so doing, I'll get rid of the pound. So this turns out to be, what is that? 20 over 0.8. 25? Something like that. And this 25 has no unit.
Yes, sir, it's 25.
25. Okay. I can do a similar trick with the specific heats. So I can divide both. This time, can you give me a hint that should I divide both by Cm or by Cw? Which one will be simpler?
CW, because
Yeah, because
that's
this
just the
there is
value
one.
of one.
Yeah, and I'll get rid of these units as well. Yeah. So if I divide both by Cw, I get rid of Cw, and I also know that Cm over Cw equals 0.1 without any units. And now it's a whole lot easier to solve this equation than the equation which we started with. Okay, so you can do that yourself, and Tf will turn out to be, just see the value, that Tf turns out to be 535 Rankine. 535 Rankine. Just go back and look at that table. 535, the final value. So 535, if I write this down, 535 Rankine, you see 1900 Rankine. The metal went from 1900 Rankine to 535 Rankine, and water went from 530 to 535 Rankine. Can you compare the changes? So how will you explain the fact that the metal bar went through a lot of change and water only changed by 5 Rankine? So who can explain that? Why is this final temperature not the middle value between these two? Why it's so, I mean, the change in water is so less compared to the change in metal. For that, you need to look at two things.
The specific heat values,
Specific heat. And there is another factor as well.
the mass also,
Mass.
the
Mass.
difference is significant.
Yeah. Because C and mass, they are both multiplying the change in temperature. If you look at the equation, in the equation, the change of temperature is being multiplied by C as well as by mass. So this product will also dictate. This product tells you this is kind of weightage. Yeah. So it turns so this tells you that water does not need so much of a change in temperature because water has a larger value of C times M. Okay, let's get to part B. In part B, you are supposed to calculate the amount of entropy produced. What is the transfer of entropy? The overall transfer of entropy, if this is your boundary, is 0. And if you think of these as subsystems, you can say that, okay, if I think of this as system 1 and this as system 2, yeah, 1 and 2, I don't need to call them 1 and 2. I just have labels M and W. So if I imagine a system M, yeah, as a subsystem, it is surrounded by W for water. So between these two, I can have now entropy transfer or heat transfer. So can you now tell me whether the entropy transfer will be from M to W or from W to M? based on what you saw so far? Knowing that entropy transfer is um, just another way of expressing the heat transfer. You divide the heat transfer by temperature, and then you call it the entropy transfer.
M to W.
Yeah, M to W, yeah. Because heat transfer is from M to W, so it must be accompanied by entropy transfer. So it means that the entropy of metal will increase or will it decrease? Because entropy is a property, yeah. So I say change in entropy for M. Can someone tell me whether this will be positive or negative? Hmm? How do you know that? If you're not sure, you can always appeal to the energy, the entropy balance. It has two terms, yeah. The change in entropy is the entropy transfer. If you remember, it was Q over T. We even had a summation, if you remember, sigma j, Tj, Qj. So because all of the metal bar is at the same temperature, we don't need a summation. So it will simply be Q over T. But remember that Q over T is um, there is a lot of detail, so we don't need to go into that detail. Yeah. We just write here the transfer, that there will be some transfer plus some production. So definitely this transfer is negative because heat transfer is away from metal, so you will have a negative term here. And this is the irreversibilities inside the metal. So if this irreversibility is insignificant compared to the transfer, then this will be negative. But we have to look for the numerical values. In case of water, it is definitely the case that delta S will be positive. Why? Delta S of water. Delta S of water will have two terms again. It will have a term arising from transfer, heat transfer from the metal, and it will have a term for production. Production is always positive, and transfer is again, in this case, it is to water from metal. So both these are positive, so this must be positive. So let's see how we can calculate this now. Um, we need to start जिस तरह यहाँ पे हमने start किया था किससे? If you remember, we started with energy balance, yeah, for the isolated system. So we now need to start with entropy balance, entropy rate balance. So I'll start with that. Entropy balance. Okay. So the change in entropy for the isolated system must equal the entropy production for the isolated system. And because it's extensive property, so I can break this down into entropy, change in entropy for the metal, plus change in entropy for water. And I have similar relationships just like this. Because entropy is an extensive property, so I can imagine that the change in entropy ds will be mass times the change in specific entropy, small s. This is small s, and that is large s. And again, I need to do this for ds metal, and I need to do this for ds water. So now I need to write something for ds metal. Now that requires me to appeal to incompressibility again. Remember, for incompressible, um, but before that, before we appeal to incompressibility, just try to recall those two equations. Remember, we had the Tds equations, yeah? Tds equations. This S is small. One was starting with U, and one was starting with H, internal energy and entropy. If I remember it correctly, this was U plus something, and this was H minus something, and this was P. I remember, okay, this was du as well. Okay, dH and du. This was PdV, and this was VdP. Huh? Yeah, if I remember this correctly. So if I if they are incompressible, which of these two equations is useful for this problem? Can somebody tell me now? Hmm? I have two equations, and I remember why do I start with these two equations? Because I need the change in entropy. So I will use either the first equation or the second equation. If I want to appeal to incompressibility assumed in this problem, yeah, which of these two equations will be relevant to me? The first one, yeah, because the first one means that dv is 0, yeah. So I will just forget about the second equation, and I will forget about this term. I will divide both these sides by t. So it's ds equals to du over t, and I have to do this for mass for metal as well as for water. I already know. Okay, there's one more thing, I think. Um, okay, I also know that du actually in the first part, in part A, I used these two constants, and that was related to du. So du is actually c times dt. Yeah. So it's c dt over t, and of course this whole thing must be done for metal separately and for water separately. So if I want to do it for water, for metal, it will be cm and dt over t for m. Yeah? But I am interested in the actual change. Yeah, I'm interested in the actual change. So for the actual change, I need to integrate. So what should I do? I will now start with this equation. I will integrate this, and that will give me delta entropy small s for metal, and cm is out of the integral, and the integral of dt over t is, if you remember it, it will be log of temperature. and the final temperature is Tf, and the initial temperature is Tmi. So you know log of Tf over Tmi is the difference, and I got this. I got the answer. If I follow the same reasoning, delta S for water will be C water, and it will be log of Tf over T Wi. So I can now add these two. I can add these two here, and this sum will give me the entropy produced, because entropy produced for the whole system is just the sum of two entropies. Entropy is an extensive property. That is something you can do yourself. इस जितनी भी रीजनिंग मैंने की है यहाँ पे आ गया, ठीक है. Remember, this log of T F over TW is what I was talking about. You must multiply this with the constant, and then you must multiply this with mass, because you need the actual entropy. You don't need the entropy per unit mass. So all this stuff here, and it turns out that the entropy, and you can now see that this is the overall entropy production, 0.0864. One term is positive, one term is negative. So this positive term is, before even looking at this detail, this positive term must correspond to water, and this negative must correspond to metal. You can check that, because I know metal got colder, so it experienced a change in a decrease in entropy, and this experienced an increase in entropy. Okay. Now this section is a quick section about the statistical interpretation of entropy, and for that we need to I'll just wait for this azan to end, and in the meantime we can think about something. Okay, so now we need, in this section there will be no numerical, but at least we'll try to have some feeling of what we mean by the connection of probability with the entropy, and why we use the term disorder. Yeah. So when you say that entropy is a measure of disorder, so we need to find out what we mean by this disorder, huh? Because this disorder thing is misinterpreted by many people. So it will turn out at the end of this discussion that this disorder is microscopic disorder. Okay, it is not macroscopic disorder. What I mean by that is that if you start with a room and you have books organized on a table, and somebody comes to your room and he just throws those books around on the floor, you cannot say that the entropy changed or entropy increased, because this is not a disorder in a microscopic sense. Yeah? Book is not a molecule. Okay, so you will see that what we mean by entropy as a measure of disorder, it's only in the sense of microscopic world. Now, to get a feel for that, before I get to this, if I now ask you, what is the relationship? Don't look at the picture, okay? Just try to recall something which you studied in that course of probability. Uh, what is the connection between probability and I would say uncertainty. Yeah. If you are uncertain about something, if you are more uncertain about something, what probability will you assign to it? And if you are certain about something, what probability will you assign to it? Okay, so keep this in mind. So if you
सर
have this
वन जब अनसर्टेन हो तो
uncertain हो तो आप क्या assign करेंगे? 1. Let's get to the specifics. Yeah, ये मैंने क्लास में बताई थी बात. You let's say there are two possibilities. Yeah, you have a friend. Let's say you have a friend in your class. So let me just write this down. You have a friend, and let's say, yeah, this is your friend. And I ask you that there are two possibilities for your friend. Either he will get an A or he won't get an A. Something other than A, yeah, less than A, B, C, or so on. Or maybe just keep it simple, yeah. Whether he will pass the course or whether he gets an F or whether he will pass. There are only two possibilities, yeah. Two possibilities because I want to keep this discussion simple. Now, if you know your friend very well, what will you tell me?
सर कि वो पास हो जाएगा
Huh? What will be the probability? What will be your probability for this question?
सर वन
1.
मतलब
ठीक है ना?
वन ही होगी सर क्योंकि हमें पता है वो पास हो जाएगा
अच्छा, और अगर आप ये कहते हैं कि 0 है तो आप फिर उसको नहीं जानते?
सही है ये भी पॉइंट है सर
ये मैं ना. So any value 1 or 0, both of these values means that you know him very well. ठीक है ना? So 1 or 0
यस सर
दोनों के केसेस में there is no uncertainty. No uncertainty. ठीक है? चाहे आप 1 असाइन
ओके
करें,
सर
चाहे आप 0 असाइन करें. अच्छा, अब आप मुझे बताएं कि आपको उसके बारे में बिल्कुल नहीं पता, फिर आप क्या असाइन करेंगे?
जीरो फेल हो जाएगा उसमें हम अनसर्टेन है सर कुछ भी हो सकता है
ये तो बताया ना, मैक्सिमम अनसर्टेनिटी. मैक्सिमम अनसर्टेनिटी कब होगी? जब आप कौन सी प्रोबेबिलिटी असाइन करेंगे? लेट मी राइट सम वैल्यूज. ओके, लेट्स से मैं डिफरेंट दोस्तों से पूछता हूँ. एक कहता है 1, दूसरा कहता है 0, एक कहता है 0.2, दूसरा कहता है 0.8 और एक कहता है 0.5. इनमें से सबसे ज्यादा अनसर्टेनिटी किस में है? हम्म
0.2.
0.2 में सबसे ज्यादा अनसर्टेनिटी है. अच्छा, मुझे लेट मी पुट इट दिस वे. The uncertainty associated with 0.2 and 0.8, is there any difference between these two answers as far as uncertainty is concerned?
Not
No,
really.
नहीं है ना.
नो
तो
सर
जिस तरह 1 और 0 सेम है,
0.5
तो 0.5 means that you have maximum uncertainty. क्योंकि आप you are undecisive. 0.2 में 0.2 and 0.8 reflect something that you know your friend to some extent. तभी तो आपने 0.5 के अलावा कोई probability assign की है ना. समझ आ गई बात? ये है. Now if I now expand this example, yeah, let me expand this example to another scenario where I again have your friend, but this time instead of asking you about pass or fail, I ask about, let's say, 12 grades. Yeah, 12 grades है मेरे पास. A plus A, B plus and so on. तो ये कितने ग्रेड्स होते हैं टोटल? 12 grades होते हैं. ठीक है. So if I now ask you to assign probabilities and plot a distribution, यहाँ पे ग्रेड है, ठीक है ना, a प्लस a माइनस अप टू f। तो अब मुझे बताएं कि ये जो प्रोबेबिलिटीज आप असाइन करेंगे, आप मुझे बताएं, टू कट द लॉन्ग स्टोरी शॉर्ट, मैक्सिमम अनसर्टेनिटी के लिए ये प्रोबेबिलिटी असाइनमेंट आप कैसे करेंगे?
यूनिफॉर्म कर देंगे डिस्ट्रीब्यूशन,
यूनिफॉर्म कर देंगे, और सबकी वैल्यू क्या होगी?
1/12.
1/12, because any distribution other than uniform means that you have some degree of certainty. So it's very established, common sense, you don't need to prove that. ठीक है? Now with this understanding, let's attack this problem on the left. So part A में आपको क्या नजर आ रहा है पिक्चर देख के? You have a tank and you have a partition, and one part is empty, there's nothing, or you have somehow evacuated it, and in the other half of the tank you have uh, molecules of some gas. And let's assume ideal gas for simplicity, okay? And you see some properties. This is the microscopic world, and the macroscopic properties you see, let's say U1 is the internal energy, T1 temperature, V1 is the volume, S1 is the entropy. ठीक हो गया? और उसके बाद अब क्या करते हैं, you remove the partition, and what happens, as you expect, the whole tank, all the volume is occupied by the gas now. और प्रॉपर्टीज को गौर से देखें, इंटरनल एनर्जी चेंज नहीं हुई, ठीक है, सिस्टम की इंटरनल एनर्जी चेंज नहीं हुई, क्यों? कैन एनीवन टेल मी व्हाई द इंटरनल एनर्जी डिड नॉट चेंज इन दिस केस? तो इसके लिए क्या, वी अस्यूम आइडियल गैस बिहेवियर। आइडियल में आपको पता है कि इसमें ये दे डोंट लूज एनर्जी, ठीक है, और देयर इज नो वर्क ट्रांसफर एंड सो ऑन। टेम्परेचर भी चेंज नहीं हुआ, ठीक है। इसमें बाद में आते हैं कि इसने क्यों कहा, और वॉल्यूम डबल हो गया, ठीक है। सो वॉल्यूम इज द प्रॉपर्टी विच डबल्ड। मैं अगर आपसे ये पूछूं पार्ट ए के लिए, लेट मी नाउ आस्क दिस, जिस तरह फ्रेंड के बारे में क्वेश्चन पूछ रहा था, नाउ आई वांट यू टू असाइन प्रोबेबिलिटीज to these two situations. On the x-axis I have the position, yeah, position नहीं बल्कि मैं कहता हूं कि partition, लेफ्ट और राइट है। मैं यहां पे लिखता हूं पार्टीशन की दो वैल्यूज हैं, लेफ्ट राइट, एंड नाउ आई आस्क्ड यू टू से समथिंग अबाउट एनी मॉलिक्यूल। सो प्रोबेबिलिटी में आपको एक्सपेरिमेंट का पता होना चाहिए। एक्सपेरिमेंट ये है, यू पिक ए मॉलिक्यूल एट रैंडम, pick a molecule at random and observe to which side, yeah, of this partition you see the molecule. तो एक पॉसिबल वैल्यू लेफ्ट है, एक पॉसिबल वैल्यू राइट है। तो आप मुझे बता सकते हैं कि आप कौन सी प्रोबेबिलिटी असाइन करेंगे इस डायग्राम में किसी भी मॉलिक्यूल के लिए? पिक एनी मॉलिक्यूल एट रैंडम। What is the probability at left that the molecule is to the left of the partition? No probability.
0.5 नहीं होगी यहाँ?
पार्ट ए में क्या है मुझे बताएं।
पार्ट ए में तो डिटरमिनिस्टिक है ना, तो लेफ्ट पे नहीं हो सकते।
हाँ, तो प्रोबेबिलिटीज क्या क्या आप असाइन करेंगे? 0, और यहाँ पे क्या होगी, क्या होगी प्रोबेबिलिटी? 1, बिकॉज यू नो इट कैन नॉट बी टू द लेफ्ट, ठीक है ना। और ये सिंपल क्वेश्चन मैं पूछ रहा हूँ, मैं यहाँ पे नहीं पूछ रहा कि इधर कौन सी होगी इधर कौन सी होगी, दैट विल कॉम्प्लिकेट द मैटर। अब यही क्वेश्चन मैं अगर आपसे पूछ लूं, एक्सपेरिमेंट वही है, कंडीशन चेंज हो गया ना, ये कंडीशनल प्रोबेबिलिटी है बेसिकली, वही एक्सपेरिमेंट है, टेक ए मॉलिक्यूल एट रैंडम, लेकिन नाउ यू हैव डिफरेंट कंडीशन। तो अब यहाँ पे आप की प्रोबेबिलिटी क्या होगी, लेफ्ट और राइट वाली? वो इमेजिनरी मैंने पार्टीशन यहाँ पे इमेजिन किया हुआ है, लेकिन है नहीं, तो अब बताएं क्या प्रोबेबिलिटी होगी, बताएं।
0.5 0.5
0.5, ये 0.5 की वैल्यू आपके पास कहाँ से आई, मुझे बताएं। एंड डू नॉट मिक्स दिस।
मैक्सिमम अनसर्टेनिटी से।
नहीं, वो तो आई है, लेकिन फॉर एग्जाम्पल,
मतलब इधर we are maximum we're completely uncertain which side there will be.
ठीक है, नहीं लेकिन इसकी वजह क्या है, कैन यू टेल मी द फ्रॉम द डिटेल्स। यहाँ पे मैं
Because of the random motion of the particle.
नहीं, वो तो है, वही रैंडम मोशन में मैं थोड़ा सा कंडीशन चेंज करूंगा और ये वैल्यूज चेंज हो जाएंगी। ये पार्टीशन बीच में था ना, ये
Oh, equally हाँ बिल्कुल बीच में
इट इज द रीजन इज दिस इक्वेशन बेसिकली V2 is equal to 2V1, क्योंकि पार्टीशन बीच में था ना, पार्टीशन बीच में था, तो the new volume is double the previous volume। अगर ये पार्टीशन यहाँ पे होता, ठीक है, ये यहाँ पे होता और आप उसको रिमूव करते और ये सारे मॉलिक्यूल्स अंदर होते इधर, ठीक है, तो फिर ये 0.5 ना होती, फिर one of them will be 1/4 and the other will be 3/4, ठीक है। So you are using actually that knowledge। अब आप मुझे बताएं कि can you now tell me why he has suggested that the entropy has increased and how you connect it to the discussion on the right hand side? How would you explain that? So this suggests that the entropy is a measure of uncertainty. The uncertainty has increased. You have less uncertainty here and you have more uncertainty here. So अब आपको समझ आएगी कि डिसऑर्डर क्यों यूज किया जा रहा है वर्ड, ठीक है, और ये इसलिए है कि हम माइक्रोस्कोपिक की बात कर रहे हैं, ठीक है, माइक्रोस्कोपिक डिसऑर्डर। अब अगर मैं इसको जस्ट टू मेक श्योर दैट वी डू नॉट मिक्स दिस विद मैक्रोस्कोपिक डिसऑर्डर, मेरे पास लेट सपोज ये एक टैंक है, ठीक है, ये ऐसे पड़ा हुआ है और इसी तरह का एक टैंक है, वो ऐसे पड़ा हुआ है, ठीक है ना, और इसी तरह मैंने ये पार्टीशन किया हुआ है और एक टैंक ऐसे पड़ा हुआ है, और कोई आके इन टैंक्स को जो है ना वो किसी को रोटेट कर देता है, रैंडमली उनको रोटेट कर देता है। So will your uncertainty change just because you have rotated some of those tanks? Will the entropy increase?
No.
No, because
Yeah, the entropy.
it was the same। वो जो आप 1 और 0 कर रहे थे, वो 1 और 0 चेंज नहीं होगा, क्योंकि that is macroscopic disorder। Macroscopic disorder has nothing to do with entropy of thermodynamics, ठीक है। So अब अगर आपको वो याद है, can you now tell me the change in entropy, कि इसमें entropy में change कितना हुआ है? If you go from this state, let's say this is state 1 and this is state 2, I went from state 1 to state 2, so you see this as a process, yeah, in which the entropy changed। So how do I calculate the change in entropy? S2 minus S1। If I assume ideal gas, yeah, I can write this as either in terms of m or in terms of n, the number of molecules, number of kilomoles, and then this will be small s2 minus small s1, yeah। और आपको याद हो कि हमने आइडियल गैस के केस में if you remember, it was ds, वही है Tds equals it was u plus pdv, du plus pdv. ठीक है? if you just remember, we used this equation previously. इसमें कौन सा जीरो होगा मुझे बताएं, इस इक्वेशन में कौन सा टर्म जीरो होगा?
du.
Because that didn't change, yeah. Okay, now how do I incorporate the ideal gas equation? Ideal gas equation is PV equals nRT, yeah. So it's actually PV, this is V bar, okay, and this is R bar, yes. So if I divide these two sides by T, I will have ds equals P over T, yeah, and from this equation P over T is nR bar over V, yes, over V bar. So I can now replace this with dV bar over V bar n times R bar. Agreed?
Yes.
Yeah, no, इसमें एक गड़बड़ मैंने कर दी है. Because I write V bar, that is automatically per kilomole, so I don't need to write this. ठीक है? ये तब होता अगर मैं यहाँ पे V लिखता, actual V. So there is no n here. Yeah. So now if I integrate this equation on both sides, what do I get? I'll get S2 minus S1 is R bar log of V2 bar divided by V1 bar. And it's the same as V2 over V1 क्योंकि उसमें कोई फर्क नहीं है. V2 over V1. So I can now plug this, and it turns out that, yeah, S2 minus S1 is R bar log of V2 over V1. What is log of V2 over V1 in this example? 2. You can even calculate that. Yes? आपने ये कोर्स पढ़ा हुआ है एडीकॉम?
जी सर, पढ़ रहे हैं
अभी पढ़ रहे हैं. उसमें एंट्रोपी, शैनन एंट्रोपी आया हुआ है अभी तक टॉपिक?
नहीं सर, अभी तक नहीं आया.
अच्छा, वहां पे जब आप पढ़ेंगे शैनन एंट्रोपी, इट विल टर्न आउट दैट शैनन एंट्रोपी, जो मैंने पहले वो फ्रेंड वाली एग्जांपल दी थी ना, दैट you have to quantify probability. You quantify uncertainty as क्योंकि आपको पता है कि it's opposite to probability है 1 over p. लेकिन 1 over p का इशू ये है कि you remember if you have independent events, their probabilities multiply, yes, but the uncertainty associated with those events or the information associated with those events, that will add up, that doesn't multiply. मैं अगर आपको 2 न्यूज़ बता देता हूं ना, मैं आपको एक न्यूज़ बताता हूं and that news has some event A, and there is another news event B. Let's say the information associated with event A is IA and the information associated with event B is IB. ये वो indicator function नहीं है, I is for information. अच्छा, and if these two news are independent, और मैं आपको दोनों न्यूज़ बता देता हूँ as a reporter, so दोनों की information आपके ख्याल में क्या होनी चाहिए if you use your common sense? Will you calculate this as AI plus B or as AI times AB? आपके ख्याल में क्या होना चाहिए? Based on what you mean by information in the day-to-day life. I told you about something, call it news A, and you say that, okay, I gained this much information by hearing that news. And then you heard another news B, IB is the news. So when you hear both news, what will a common man on the street think of the overall information associated with both? Do we associate it like this, or do we associate it like this, or any other quantity? Hmm? If you think about this, we typically think of information as being additive, because as you gain more and more information, you add the information, ठीक है ना? तो उसके लिए ये 1/p जो है ना, ये सुटेबल नहीं है, इसको आपको इसका लॉग लेना पड़ेगा, लॉग या सिंपल लॉग, मेट्रिक लॉग, या जो है ना वो नेचुरल लॉग है, ठीक है? So log of 1/p is a better measure of information and uncertainty than it is than just 1/p, ठीक है? तो ये अगर आप पढ़ लें, ये मैं डिस्कस नहीं करना चाह रहा, ये अगर आप पढ़ लें तो इसने असल में बेसिकली वो जो डिस्कशन है वो शेनन एंट्रोपी वाली, उसको कनेक्ट किया है थर्मोडायनामिक की एंट्रोपी से, एंड द कांस्टेंट लिंकिंग दीज टू, बिकॉज शेनन एंट्रोपी यू विल व्हिच यू विल स्टडी इन दिस कोर्स इज एब्स्ट्रैक्ट, वो कोई फिजिकल चीज नहीं है. Entropy in thermodynamics is a physical thing. You need some conversion factor. So Kb, the Boltzmann's constant, is that entropy, that physical entropy, which must multiply the Shannon entropy, जो कि सिर्फ information से related है, and it converts it into physical entropy. ठीक है? So I think that you should not get into this discussion. आपने check किया कि even units भी same है. So I only wanted to cover this so that you have a feeling for what do we mean by disorder. Disorder means a loss of knowledge, yeah, or an increase of uncertainty. ठीक है, ये हम नेक्स्ट सेक्शन जो है ना वो ट्यूसडे को स्टार्ट करेंगे, लेकिन ऐसा अनाउंसमेंट आपने देख ली है स्लेट पे जो आज मैंने की है?
Yes, sir. Assignment.
ठीक है, तो वो 3 क्वेश्चंस है, एंड मेक श्योर दैट यू सबमिट योर असाइनमेंट बिफोर द डेडलाइन, ठीक है? उसके बाद मुझे ईमेल ना कीजिएगा कि ये हुआ, ये स्लेट नहीं चल रहा था. जब स्लेट नहीं चल रहा था तो आप उससे एक दिन पहले ट्राई कर लें, ठीक है, या 2 घंटे पहले कर लें. अगर स्लेट ना चलने की सूरत में आप मुझे ईमेल करते तो ईमेल भी डेडलाइन से पहले हो, ठीक है ना? इट्स नॉट एक्सेप्टेबल जी, चूंकि स्लेट नहीं चल रहा था तो मैं ईमेल बाद में करूंगा, दैट्स एक्सेप्टेबल. सो ठीक है.